In this problem, we are looking at the curve y equals the square root of x plus 5 defined over the interval 1, 2. And we're asked to do two things. First of all, we're asked to subdivide this interval into 4 pieces of with delta x equals 0.25 and use the corresponding 4 line segments in order to estimate the length of this curve. The second thing we're asked to do is to compute an integral or to find an integral which will compute exactly the arc length of this curve should we evaluate it. And so let's go ahead and talk about part A to begin with. While working with part A, I want to be able to utilize the distance formula to be able to compute the length of all 4 of my segments here. So in order to do that, I need to know both the x values and the y values of all 5 of these points. And so I'm going to go ahead and compile this information into a table here. We know that our first x value is 1, since that's the start of our interval. And then we increment by values of, or delta x of 0.25. So my x values are 1.1, 1.25, 1.5, 1.75, and 2. The corresponding y values are the evaluation of these x values at f of x, which is square root of x plus 5. So that gives us outputs of 6, square root of 6.25, square root of 6.5, square root of 6.75, and square root of 7. Now, remember that in general, the distance formula between 2 points, x1, y1, and x2, y2, is the square root of x1 minus x2 squared plus y1 minus y2 squared. We also note that between my x values, that distance is a constant 0.25 each time by design. So if I want to utilize my first, or to find the distance between my first 2 points, these values here, between points 1 square root 6 and 1.5 square root 6.25, I can compute that by taking the difference in my x values, 0.25 squared, plus the square of the difference of my y values, which is root 6.25 minus root 6. And all of this under the radical gives me the length of my first segment. And I can do something similar for each of the other 3 segments. The next segment, the change in x is still 0.25 squared, and my change in y is root 6.5 minus root 6.25 squared. Plus my third segment, again, my change in x is 0.25 squared, and my change in y values is root 6.75 minus root 6.5 quantity squared. And finally, for my final segment, it's 0.25 squared plus quantity root 7 minus root 6.75 squared. Now this expression here exactly computes the length of these 4 line segments. By using our favorite technology to compute these values, we can get an estimate for this length. The first length segment is about 0.2551 units long. The second line segment is about 0.2549 units long. The third line segment is about 0.2547 units long. And the fourth line segment is about 0.2545 units long, which gives me estimated length of 1.0192. The second part of this problem asks us to find an integral that would exactly compute the arc length of this curve. So we first note in general that the arc length is going to be a definite integral over the starting and ending x values of our curve times or of 1 plus the derivative of our function, which defines the curve, quantity squared, root with respect to x. We also want to note, since our function in this case is root x plus 5, its derivative is 1 over 2 root x plus 5 times 1 by the chain rule. And so in this particular case, the arc length of the curve is an integral. Our starting value is 1, our end value is 2 of the square root of 1 plus 1 over 2 root x plus 5 squared with respect to x, which, should we choose to, we could rewrite root 1 plus 1 over 4 x plus 5 dx. All right. Thank you very much.